The summer heat shimmered over the dusty roads of Tunisia in May 1943. Hauptmann Friedrich Weber stood beside his broken-down Panzer IV, watching black smoke curl from the engine compartment. This was the third mechanical failure in 2 weeks. The same story played out across German armoured units throughout North Africa. Overheated engines, stripped gears, broken final drives. Tanks that could barely complete a 50-kilometre march without something catastrophic failing. Then Weber saw something that would change everything he believed about American engineering. Sitting in a captured equipment yard near Tunis was an M4 Sherman tank, abandoned by retreating American forces after the Battle of Kasserine Pass. The Germans had towed it back for evaluation. Weber approached the machine with the contempt bred into every German officer. American tanks were garbage. Everyone knew that. Crude. Simple. Built by a nation that understood nothing about precision engineering. The Sherman looked ungainly compared to German designs. Taller than it needed to be. Boxy. Inelegant. Nothing like the sleek, purposeful lines of a Panther or the brutal efficiency of a Tiger. This was a tank built by a country that made automobiles, not weapons. A tank designed by mechanics, not engineers. What could such a machine possibly teach the nation that had invented blitzkrieg? If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Weber's technical officer, Oberleutnant Hans Richter, had spent the previous day examining the captured Sherman in detail. His preliminary report sat on Weber's field desk that evening. What Richter had discovered contradicted everything German tank crews had been taught about American equipment. The Sherman's construction was remarkably straightforward. Large access panels, bolted assemblies, standardized parts, everything designed for rapid, field maintenance by crews with basic mechanical training. German tanks like the Panther required specialized tools and highly trained technicians for even routine maintenance. The Sherman required wrenches and common sense. Richter had opened the engine compartment and found a Continental R-975 radial aircraft engine producing 400 horsepower. Not particularly powerful compared to the Maybach engines in German tanks, but the installation was brilliant in its simplicity. The entire power pack, engine and transmission together could be removed as a single unit through large access doors in the rear hull. German tanks required the turret to be removed before the engine could be extracted. A Sherman engine change took 8 hours with a trained crew. A Panther engine change took 3 days. The transmission was a manual gearbox with 5 forward speeds and 1 reverse. Nothing sophisticated, no complicated hydraulics or precision mechanisms, just gears, shafts, and bearings, built to automotive tolerances. Richter noted that the entire transmission assembly could be replaced in the field without specialized equipment. The Panther's transmission, by contrast, required factory-level facilities to repair or replace. The suspension used vertical volute spring units, 1 per road wheel. Each suspension unit was an independent assembly that could be unbolted and replaced individually. When a Sherman threw a track or damaged a road wheel, the crew could repair it in hours using basic tools. German tanks with their interleaved road wheels and complex torsion bar systems required days of work for similar repairs. But none of this impressed Weber initially. Simple construction meant crude performance, surely. The real test would be how the machine actually functioned under combat conditions. The Germans decided to drive the captured Sherman and see how long it lasted before the inevitable American mechanical failure occurred. Obergefreiter Kurt Becker, A. experienced driver with 2 years on the Eastern Front, was selected to operate the Sherman. He had driven Panzer IIIs and Panzer IVs extensively. He understood tracked vehicles. He climbed into the driver's position, expecting the usual German layout, cramped and complicated. Instead, he found something that reminded him of driving his father's truck before the war. The controls were laid out logically. The clutch, brake, and accelerator pedals were positioned exactly where automotive practice would place them. The gearshift fell naturally to hand. The instruments were clear and readable. Everything was designed for an operator, not an engineer. Becker started the engine. The radial engine roared to life with a distinctive sound, completely different from German inline engines. It settled into a steady idle. Becker engaged the clutch, selected first gear, and released the clutch pedal. The Sherman lurched forward smoothly. He shifted to second gear. The synchronizers worked perfectly. Third gear, fourth gear. The transmission was remarkably easy to operate compared to German gearboxes that required careful double clutching and precise timing. The Sherman rolled across the test ground near the equipment yard. Becker put it through basic maneuvers. Turns, reversing, emergency stops. The steering levers required less effort than German systems. The brakes responded predictably. Everything worked exactly as expected, with no surprises or quirks. After an hour of familiarization driving, Becker reported to Weber. "Herr Hauptmann, this tank drives like a truck. Everything is simple. Everything works. I could teach a replacement driver to operate this machine in a week." Weber remained skeptical. Simple operation was fine for basic maneuvering, but what about sustained operations? What about combat stress? What about reliability over hundreds of kilometers? German doctrine emphasized technical sophistication for good reasons. Precision engineering produced superior performance. American simplicity was a weakness, not a strength. The real test began the next day. Weber ordered Becker to drive the Sherman on an extended road march from Tunis southward towards Sfax, approximately 200 kilometers. This would reveal the truth. The Sherman would break down within 50 kilometers, maybe sooner. American tanks always failed. Everyone knew this. Becker departed at dawn on May 18, 1943. A Kubelwagen followed, carrying Richter and a maintenance crew with tools, spare parts, and recovery equipment. They expected to need everything. The convoy rolled out onto the coastal road heading south. 20 kilometers passed, 30 kilometers, 50 kilometers. The Sherman continued running smoothly. The engine temperature remained stable. No unusual noises. No oil leaks. No mechanical complaints of any kind. Becker reported that the tank was performing flawlessly. Richter grew increasingly surprised. By this point in any comparable march with German armor, at least one vehicle would have developed problems: overheating, oil pressure loss, transmission difficulties. The Panther was notorious for final drive failures within the first 100 kilometers, yet the American tank simply kept going. They reached the halfway point, 100 kilometers, and stopped for fuel and a crew rest. Richter performed a detailed mechanical inspection. He checked oil levels, examined the tracks for wear, inspected the suspension units, tested the transmission for unusual heat or leaks. Everything appeared perfect. The Sherman showed no signs of mechanical stress whatsoever. This was impossible. American equipment was inferior. Everyone from Hitler down to the newest replacement soldier knew this as absolute fact. German engineering was the finest in the world. American mass production created crude, unreliable machines. Yet, here was direct evidence contradicting that certainty. They continued south. 120 kilometers, 150 kilometers, 180 kilometers. The Sherman never faltered. The engine ran smoothly hour after hour. The transmission shifted cleanly every time. The tracks remained properly tensioned. The suspension absorbed rough roads without complaint. They reached Sfax after covering 200 kilometers in a single day. Becker shut down the engine and climbed out of the driver's hatch. He looked at Richter with an expression mixing confusion and grudging respect. "Herr Oberleutnant, I have driven Panzers that broke down making this same journey. This American tank has given me no problems at all." Richter conducted another thorough inspection. He measured track wear, minimal. He checked for oil leaks, none. He tested every mechanical system, all functioning perfectly. The Sherman had completed a 200-kilometer road march under North African heat without a single mechanical issue. Weber reviewed Richter's report that evening with growing disbelief. This contradicted every assumption about American industrial capability. If the Americans could build tanks this reliable, what did that mean for the wider war? How many of these machines could American factories produce? If each one could operate reliably over hundreds of kilometers without breaking down, what advantage did German technical sophistication actually provide? The test continued. Over the next 3 weeks, Becker drove the captured Sherman on multiple extended missions throughout southern Tunisia. The Germans wanted to push the machine to failure. They needed to find its breaking point. They needed proof that American equipment was inferior. The Sherman covered 500 kilometers, 600, 700. Routine maintenance consisted of checking oil levels, topping off coolant, and adjusting track tension. Tasks that any crew could perform in less than an hour. No major repairs, no component failures, no mechanical breakdowns of any kind. German maintenance crews were stunned. They maintained Panthers that required constant attention, final drives that failed every 150 kilometers, transmissions that needed rebuilding every 1,000 kilometers, engines that overheated in hot weather and refused to start in cold weather, interleaved road wheels that jammed with mud and required hours of cleaning. The Panther was a maintenance nightmare that consumed enormous resources just to keep operational. The Sherman required almost nothing: basic automotive maintenance, oil changes, grease fittings, simple, routine tasks that took minimal time and required no specialized knowledge. After 800 kilometers, Weber ordered an engine inspection. Richter and his maintenance team removed the rear hull panels and extracted the power pack using a simple crane setup. The entire operation took 9 hours. They disassembled the engine and transmission on a field workbench. The internal components showed normal wear patterns, nothing excessive, nothing concerning. The pistons, rings, and cylinder walls were in excellent condition. The bearings showed proper oil distribution, with no scoring or spalling. The transmission gears displayed even wear with no stripped teeth or damaged synchronizers. Richter wrote in his technical report, "After 800 kilometers of operation under combat conditions in North African heat, this engine and transmission show less wear than German units typically display after 200 kilometers. The quality of American metallurgy and manufacturing precision is far higher than we have been led to believe." Weber forwarded the report up the chain of command. His superiors were not interested. The official position remained unchanged. American equipment was inferior. Any evidence suggesting otherwise was dismissed as anomalous, the result of a particularly well-built example, not representative of American production standards. But Weber could not dismiss what he had witnessed. The Sherman continued operating. 900 kilometers, 1,000 kilometers, 1,200 kilometers. Every day, Becker drove the tank on patrol routes, training exercises, and cross-country movements. Every day, the machine performed flawlessly. The reliability was extraordinary, but what impressed Weber most was the maintainability. When the Sherman finally required its first significant maintenance at 1,300 kilometers, the task was changing the oil and adjusting the clutch. Becker and one assistant completed the work in 3 hours using standard tools, no specialized equipment, no technical manuals beyond basic operator instructions, no engineers or factory technicians required. Compare that to maintaining a Panther. The Maybach HL 230P30 engine required oil changes every 500 kilometers, but accessing the oil system required removing multiple panels and components. The cooling system needed constant monitoring because overheating was endemic. The final drives failed so regularly that replacement units were stocked at battalion level as consumable supplies. The Sherman's design prioritized ease of maintenance over technical sophistication. Every major component was accessible through large panels. Every assembly used standard fasteners and fittings. Everything was designed so that moderately trained crews could perform repairs in the field without specialized support. Richter documented this philosophy in detail. American designers understood that tanks would operate far from factories and supply depots. They understood that combat would damage equipment. They understood that crews needed to perform repairs quickly under difficult conditions, so they designed every system with maintenance, accessibility as a primary requirement. German designers, by contrast, prioritized performance over maintainability. The Panther's interleaved road wheel system provided excellent weight distribution and ride quality, but made track maintenance incredibly difficult. The torsion bar suspension offered superior performance, but required major disassembly to repair. The Maybach engine produced excellent power, but was packaged so tightly that accessing components for maintenance was extremely challenging. The Americans accepted slightly lower peak performance in exchange for dramatically better maintainability. The Sherman's suspension was simpler and easier to service. The engine was less powerful but far more accessible. The transmission was conventional but could be replaced in hours rather than days. This design philosophy reflected fundamentally different approaches to warfare. German doctrine emphasized technical superiority to compensate for numerical inferiority. Build better tanks than the enemy even if you cannot build as many. Accept complexity, because properly trained crews can handle it. Prioritize combat performance over logistical considerations. American doctrine emphasized sustainability and reliability. Build tanks that work consistently. Design for mass production. Ensure that average crews can maintain and repair equipment. Accept adequate combat performance if it comes with superior operational availability. By 1400 kilometers, the Sherman had proven which philosophy worked better in practice. The tank continued operating with minimal maintenance. Becker reported that it was more reliable than any German tank he had ever driven. The engine never overheated. The transmission never failed. The suspension never broke. The tracks lasted far longer than German tracks before requiring replacement. Weber compiled a comprehensive assessment for his division commander. He documented every kilometer driven, every maintenance action performed, every component inspected. The conclusion was inescapable. The American Sherman was a more reliable fighting vehicle than anything in the German inventory. The response from higher headquarters was harsh. Weber was informed that his assessment was defeatist. He was spreading enemy propaganda. The Sherman's apparent reliability was a trick, a deception, the result of examining a single vehicle that was not representative. American tanks were inferior. This was established fact, supported by the Führer himself. Weber was ordered to stop his testing and destroy the captured Sherman immediately. Weber complied. The Sherman was driven to a firing range and used as a target for German anti-tank guns. Even in destruction, it taught lessons. The 75mm frontal armor was relatively thin compared to German designs. Anti-tank rounds penetrated easily, but the crew compartment layout provided multiple escape routes. The large hatches allowed rapid crew evacuation. The wet ammunition storage system, which Weber's men had noted earlier, prevented catastrophic ammunition fires even when the tank was penetrated. The Sherman burned, but it did not explode. The crew would have had time to escape. Tanks with their internal ammunition storage regularly suffered catastrophic explosions that killed entire crews instantly. Becker watched the Sherman burn with an expression Weber could not quite read. Later, the driver said quietly, "Herr Hauptmann, that was the best tank I ever drove. If Germany built tanks like that instead of Panthers and Tigers, maybe we would win this war." Weber did not respond. What could he say? The truth was too dangerous to speak aloud, but he understood what Becker meant. The Sherman represented everything German armored forces needed but did not have: reliability, maintainability, simplicity, sustainability. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The broader implications of Weber's testing went far beyond one captured tank. His 1,400-kilometer test proved that American industrial methods produced reliable military equipment at a level German industry could not match. This was not about raw specifications or technical sophistication. This was about fundamental engineering philosophy and manufacturing quality. American tanks were designed by automotive engineers who understood that vehicles needed to operate reliably over thousands of miles with minimal maintenance. They applied lessons learned from commercial truck production. They prioritized durability, accessibility, and ease of repair. They accepted standardized components and conventional designs because those approaches worked. German tanks were designed by weapons engineers who prioritized combat performance above all else. They pushed technical boundaries, pursuing maximum armor protection and firepower even when those goals created maintenance nightmares. They accepted complex systems because complexity enabled capabilities. They designed for technical excellence without adequately considering sustainability. The results spoke clearly. American factories produced 49,324 Sherman tanks between 1942 and 1945. German factories produced approximately 6,000 Panthers during the same period. The Sherman could be manufactured using conventional automotive production methods. The Panther required specialized facilities and skilled labor that Germany increasingly lacked. More importantly, those 49,000 Shermans operated reliably enough to sustain combat operations continuously from North Africa through Sicily, Italy, France, and into Germany itself. The 6,000 Panthers suffered such catastrophic mechanical failure rates that German armored divisions could rarely field more than half their authorized tank strength at any given time. Weber's test revealed this truth in microcosm. The Sherman he evaluated ran 1,400 kilometers without major mechanical issues. A Panther would have been extraordinarily lucky to complete half that distance before suffering final drive failure, transmission breakdown, or engine problems. This reliability gap translated directly into operational capability. An American armored division could conduct sustained advances covering hundreds of kilometers over days or weeks. Shermans would reach objectives, fight battles, and continue operating. German armored divisions had to factor in massive mechanical attrition during any extended movement. Panthers broke down en route to battles, during battles, and while withdrawing from battles. The German military leadership refused to acknowledge this reality. Official assessments continued, claiming German technical superiority. Propaganda emphasized the Panther's powerful gun and thick armor while ignoring its mechanical weaknesses. Field commanders requesting more reliable equipment were told to make do with existing vehicles and stop complaining. But frontline troops knew the truth. They lived with broken-down Panthers littering roads behind every advance. They watched recovery crews struggle to tow 70-ton King Tigers that had thrown tracks or suffered transmission failures. They experienced the frustration of planning operations around expected mechanical failure rates rather than enemy opposition. Meanwhile, they observed American forces operating with a reliability that seemed almost supernatural. American tank columns advanced day after day without stopping. When Shermans were knocked out by enemy fire, replacement tanks arrived from supply depots within days or hours. When Shermans required maintenance, crews performed it quickly in the field and continued operations. This created a psychological effect beyond mere tactical impact. German tank crews began to understand that they were losing not because American tanks were superior in direct combat. The Panther's gun and armor still provided advantages in tank versus tank engagements, but because American tanks actually worked consistently, while German tanks did not. The industrial implications were even more devastating to German prospects. American production methods could be scaled almost infinitely. Factories across the United States built Shermans using assembly line techniques perfected for automobile manufacturing. Chrysler, Ford, General Motors, American Locomotive Company, and others produced tanks at rates Germany simply could not match, regardless of effort or resources invested. German production methods for the Panther required specialized machinery, skilled craftsmen, and precision manufacturing that could not be easily expanded. Allied bombing targeted German tank factories, disrupting production and destroying tooling. By late 1944, Panther production was declining, even as demand increased desperately. The Americans could replace tank losses faster than Germans could inflict them. Every destroyed Sherman was replaced by 2 more arriving from American factories. Every destroyed Panther represented an irreplaceable loss that weakened German armored forces permanently. Weber understood all of this by the time his captured Sherman burned on that firing range. He had documented the evidence. He had proven American reliability. He had demonstrated that German assumptions about technical superiority were dangerously wrong, and he had been ordered to shut up and destroy the evidence. His report disappeared into the military bureaucracy, ignored and suppressed because it contradicted official narratives. The 1,400 kilometers that Sherman had traveled, carrying a German crew in perfect reliability, those kilometers proved nothing to men who refused to see. But among the German tank crews who had witnessed the testing, word spread. They had watched the American tank operate day after day without breaking down. They had seen German mechanics unable to find anything wrong with it after hundreds of kilometers. They had recognized that what they had been told about American inferiority was a lie. That recognition would haunt them in the battles to come, when their own Panthers sat broken beside roads while American Shermans rolled past them toward Berlin. The story of Weber's captured Sherman encapsulated the entire strategic dynamic of the Second World War's armored warfare. Germany built technically sophisticated tanks that impressed on paper but failed in practice. America built adequately capable tanks that worked reliably and could be produced in overwhelming numbers. Technical sophistication without reliability is useless. Impressive specifications without sustainable logistics is meaningless. The best tank in the world provides zero combat power if it cannot reach the battlefield, cannot operate when it arrives, and cannot be repaired when damaged. The Germans learned this lesson too late, if they ever truly learned it at all. Their Panther tanks, King Tigers, and other advanced designs consumed resources that could have built 3 times as many simpler, more reliable vehicles. Those sophisticated tanks broke down constantly, required specialized maintenance they could rarely receive, and were eventually abandoned when fuel or spare parts ran out. The Americans understood from the beginning that wars are won by systems, not by individual weapons. The Sherman was one component of an integrated system that included reliable logistics, efficient production, effective maintenance, and sound doctrine. That system worked. It sustained multi-year campaigns across multiple continents. It brought victory. The lessons Weber learned watching that Sherman operate for 1,400 kilometers without significant problems were lessons the German military should have learned years earlier. But institutional inertia, ideological certainty, and Hitler's personal interference in tank development prevented rational assessment of what actually worked versus what looked impressive. German tank development followed a consistent pattern throughout the war. Encounter, enemy capability. Overreact by designing something far more sophisticated and complex. Rush into production before testing adequately. Discover catastrophic mechanical problems in the field. Attempt fixes that never fully address fundamental design flaws. Watch operational readiness rates plummet, while maintenance requirements skyrocket. The Panther exemplified this pattern perfectly. After German forces encountered Soviet T-34 tanks in 1941, the response was immediate and extreme. Design a medium tank that could defeat the T-34 inches every measurable category. Bigger gun, thicker armor, higher speed, better optics, superior firepower at range. The design commission that created the Panther prioritized these combat specifications above everything else. They accepted a final weight of 45 tons, even though the transmission and final drives were designed for a 35-ton vehicle. They accepted complex interleaved road wheels because that system distributed weight better, ignoring the maintenance nightmare it created. They accepted a powerful but temperamental engine because peak performance mattered more than reliability. The result was a tank that excelled in direct combat when everything worked, but suffered mechanical failure rates that crippled German armored operations. French post-war evaluation of captured Panthers documented average final drive life of only 150 kilometers. Soviet testing showed similar results. British attempts to operate Panthers post-war found them so unreliable that standard acceptance trials could not be completed. The Sherman development process followed an entirely different philosophy. American designers started with a clear understanding of operational requirements. The tank needed to be produced in large numbers using existing industrial capacity. It needed to be reliable enough for sustained operations over hundreds of miles. It needed to be maintainable by average crews with standard tools. It needed to be transportable by ship across oceans. These requirements drove every design decision. The Continental R-975 radial engine was selected because it was already in production for aircraft, proven reliable, and could be manufactured in quantity. The transmission was conventional automotive design because that approach was reliable and well understood. The suspension used vertical volute springs because that system was simple, effective, and easy to maintain. Combat capability was certainly important. The 75mm gun provided adequate anti-tank performance and excellent high-explosive effectiveness. The armor protection was sufficient against most German weapons at normal combat ranges. But these combat capabilities were never pursued at the expense of reliability, maintainability, or producibility. The American approach reflected lessons learned from decades of automotive manufacturing. Henry Ford's assembly line techniques demonstrated that standardization and simplicity enabled mass production. General Motors' experience with commercial trucks proved that reliable mechanical design was achievable through conservative engineering and quality manufacturing. These industrial giants brought their expertise to tank production, creating weapons that worked consistently because they were built using proven methods. German industry lacked this automotive manufacturing experience at scale. German car production before the war focused on smaller numbers of higher quality vehicles. Volkswagen was attempting to create mass production capability, but the war interrupted that development. German heavy industry excelled at precision engineering for ships, locomotives, and heavy machinery. But these industries emphasized craftsmanship and technical sophistication over mass production efficiency. When tasked with building tanks, German industry applied the engineering philosophy it knew: precision manufacturing, complex systems, technical excellence. These approaches produced impressive machines that performed brilliantly when everything worked perfectly, but they also produced machines that required constant expert attention, consumed resources at unsustainable rates, and broke down under operational stress. The captured Sherman that Weber tested represented everything German tank design was not. It was simple where German tanks were complex. It was reliable where German tanks were temperamental. It was maintainable where German tanks were finicky. It was producible where German tanks required specialized manufacturing. Every one of these differences traced back to fundamental design philosophy. American designers accepted adequate performance in exchange for exceptional reliability. German designers pursued maximum performance even when it compromised reliability. In sustained combat operations spanning years and continents, the American approach proved decisively superior. The strategic arithmetic was brutally simple. American factories produced approximately 50,000 Sherman tanks. German factories produced approximately 6,000 Panthers, 1,500 Tigers, and 500 King Tigers. Even if German tanks were twice as effective in direct combat, which they arguably were not considering their mechanical problems, the numerical advantage was overwhelming. But the numbers were even more lopsided than raw production figures suggested. Of those 50,000 Shermans, the vast majority operated reliably enough to reach combat, fight effectively, and continue operating afterward. Of those 6,000 Panthers, roughly half were non-operational at any given time due to mechanical failures. The operational ratio was not 50,000 Shermans against 6,000 Panthers. It was 50,000 mostly reliable Shermans against 3,000 sometimes functional Panthers. Weber understood this after his testing concluded. He had watched one Sherman operate flawlessly for 1,400 kilometers. He knew from direct experience that German tanks could not match that reliability. He understood the implications for the broader war. Germany was losing the industrial competition decisively. No amount of technical sophistication could compensate for the reliability and production advantages America possessed. His superiors did not want to hear this assessment. They preferred comforting lies about German technical superiority to uncomfortable truths about industrial inadequacy. So Weber's report was buried, his testing was terminated, and the Sherman was destroyed to eliminate the evidence. But truth has a way of asserting itself, regardless of official denials. As the war progressed, more German units captured American tanks. Some attempted to use them operationally. The experiences were remarkably consistent. The Shermans worked. They ran reliably. They required minimal maintenance. They were easy to operate. Every German crew that spent time in a Sherman came away, impressed by its mechanical reliability. Meanwhile, German crews struggling with Panthers and Tigers grew increasingly frustrated. They watched their sophisticated machines break down repeatedly. They waited days or weeks for spare parts that never arrived. They performed field maintenance that should have been done at depot level, because no depots were accessible. They abandoned tanks after relatively minor failures because repairs were impossible under field conditions. The psychological impact was devastating. German propaganda had promised that superior German engineering would overcome Allied numerical advantages. German tank crews had been told their Panthers and Tigers were invincible war machines that would restore German battlefield dominance. The reality was tanks that broke down more often than they fought, that consumed fuel they did not have, that required maintenance they could not perform. American tankers, by contrast, developed confidence in their equipment. Yes, the Sherman's armor was thin. Yes, German guns could penetrate from long range, but American crews trusted that their tanks would start every morning, would operate reliably throughout the day, and would be repairable when damaged. That trust enabled aggressive tactics. Commanders knew they could execute multi-day operations without massive mechanical attrition. Crews knew they could maneuver boldly because their tanks would respond reliably. This confidence differential was as important as any technical specification. German crews in Panthers had to factor mechanical unreliability into every tactical decision. How far could they advance before something broke? Would the tank make it back to friendly lines if they had to withdraw? Could they trust the engine in an emergency? These doubts constrained German operations in ways that had nothing to do with enemy action. American crews faced no such doubts. The Sherman would work. It always worked. That certainty enabled operational tempo that Germans could not match. American armored divisions advanced continuously, covering hundreds of kilometers in sustained operations. German armored divisions moved in fits and starts, advancing until mechanical failures forced halts for recovery and repair. The Battle of the Bulge in December 1944 provided the ultimate demonstration of this dynamic. German forces launched a massive counteroffensive with approximately 1,500 tanks and assault guns, including significant numbers of Panthers and King Tigers. The offensive plan required rapid advances to capture fuel depots before German tanks ran out of diesel. What actually happened was a mechanical catastrophe. Panthers broke down en route to their start positions. King Tigers threw tracks during approach marches. Those that reached combat consumed fuel at rates that German logistics could not sustain. Within days, German armoured spearheads ground to a halt, not because of enemy resistance, but because of mechanical failures and fuel exhaustion. American forces responding to the attack moved entire armoured divisions, hundreds of kilometres in winter conditions. Their Shermans operated reliably in freezing temperatures that would have crippled German tanks even if fuel had been available. American maintenance crews performed field repairs quickly and efficiently. American logistics delivered fuel, ammunition, and spare parts continuously. By early January 1945, the German offensive had collapsed completely. American forces advancing through the Ardennes found abandoned German tanks littering the roads. Many showed no combat damage. They had simply broken down or run out of fuel and been abandoned by their crews. Panthers with thrown tracks, King Tigers with seized engines, Jag Panthers with failed transmissions. The contrasting reliability was stark. American after-action reports noted that more German heavy tanks were captured intact or abandoned than were destroyed by American fire. The vaunted German armour that was supposed to restore German battlefield dominance had been defeated primarily by its own mechanical unreliability. This pattern repeated across every theatre where German and American armour met. In Italy, German tanks struggled with mountainous terrain that overstressed their drivetrains. In France, German armour could not sustain the pace of mobile operations. In Germany itself, Panthers and Tigers sat immobilized for lack of fuel, while Shermans rolled past them toward Berlin. The Americans who captured intact German tanks and examined them closely came away with consistent observations. Impressive guns, thick armour, sophisticated systems, but fundamentally flawed execution that prioritized specifications over reliability. American ordnance officers compiled detailed technical intelligence reports on every captured German tank type. These reports documented the mechanical problems in exhaustive detail. The Panther reports noted the final drive failures, the transmission problems, the engine reliability issues, the maintenance difficulties. The King Tiger reports documented even worse problems, with mechanical failure rates so severe that most King Tigers were abandoned before reaching combat. The reports concluded that German tanks were certainly dangerous when they worked, but were far less effective operationally than their specifications suggested. These assessments influenced American post-war tank development significantly. American designers learned what not to do from studying German failures. They learned that over-optimization for specific capabilities creates systems that fail under stress. They learned that complexity without corresponding reliability produces unusable weapons. They learned that impressive specifications mean nothing if the vehicle cannot be sustained operationally. The M46, M47, M48, and M60 tanks that America developed after World War II all reflected lessons learned from the Sherman's success and the Panzer's failure. Reliability was prioritized as a fundamental requirement. Maintainability was designed in from the beginning. Simplicity was valued over sophistication. These principles created tanks that worked consistently in combat operations spanning decades. The M48 served effectively through the Vietnam War. The M60 remained in frontline service into the 1990s. Both designs prioritized the same factors that made the Sherman successful: reliability, maintainability, and sustainability over maximum technical performance. Both proved far more effective operationally than more sophisticated designs from other nations that pursued performance over reliability. The story of Weber's captured Sherman testing in Tunisia encapsulated these broader lessons in a single 1,400-kilometer journey. That one American tank, operated by German crews under combat conditions, demonstrated conclusively that reliability matters more than sophistication. That sustainable design triumphs over impressive specifications, that wars are won by systems that work consistently, not by weapons that excel briefly before breaking down. 79 years later, the lesson remains profoundly relevant. Military equipment must function reliably under the worst conditions. It must be maintainable with available resources and infrastructure. It must be producible in quantities that meet operational demands. It must account for human factors in operation and maintenance. Technical excellence that ignores these requirements produces expensive failures that collapse under operational stress. The Sherman succeeded because it embraced these principles completely. The Panther failed because it ignored them consistently. Weber recognized this truth after 1,400 kilometers of testing. He documented the evidence. He reported his findings. He was ignored by superiors who preferred comfortable lies to uncomfortable truths. But the truth asserted itself regardless. American Shermans rolled into Berlin in May 1945, while abandoned German Panthers littered the roads behind the retreating Wehrmacht. The verdict was clear. Reliability had defeated sophistication. Sustainability had triumphed over technical specifications. The simple American tank that German officers had mocked as crude and unsophisticated had proven vastly superior to the complex German machines that looked impressive on paper but failed catastrophically in practice. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.